So we are in the last phase of our fins chapter. So if you just recall, we had found the temperature distribution of the fins for various conditions. In fact, to be very clear, we just put the fins. We had put the fins for the sake of increasing the surface area. That is why this is called as extended surface. So we wrote the general conduction equation. We solved that equation for various scenarios, and that is, it can be for any shape. It can be rectangular fin, pin fin, triangular fin, any of the fins. We assumed cross sectional area. For the constant cross sectional area, we derived the temperature distribution and also the heat transfer rate. So this is for infinitely long fin, this is for prescribed temperature, adiabatic condition, convective heat transfer. So we got not only the temperature distribution but also the fin heat transfer rate, and both are important, as I told you in the last class while solving the problem. It's just not the temperature but also the heat transfer which is important. So the question is, what should be the proper length of the fin? So both can be addressed, that is, the proper length of the fin can be addressed through efficiency also. So you can see that the temperature of the fin is following exponentially, although ideally if you were to have highest thermal conductivity or the infinite thermal conductivity, the temperature will not fall, it will be uniform. But there will be finite thermal conductivity for any material. In that case, the temperature is going to fall. So only for a particular length my fin is effective or efficiency is good, beyond which the efficiency is going to be lowering itself. So it's not worth it putting a fin beyond a certain length because of the cost considerations. So to address this, so we compared Q fin with an adiabatic fin tip with the infinitely long fin, and we found the tan hyperbolic ml it comes to. So tan hyperbolic ml is roughly around, for an ml of 2.65, tan hyperbolic ml is 1. So if you choose an ml of 2.65, so you get tan hyperbolic ml of 1. So you would not like to use an ml beyond 2.65. So now with this, armored with this, we solved a problem, and we took three materials, that is stainless steel, aluminum and copper, and this is the temperature distribution for an infinitely long fin we got. With just the temperature distribution we cannot make a choice, so we computed the heat transfer rate or the dissipation rate from each of the fin. You can find that the copper fin dissipates 8.3 watts for a length of 0.19 meters. Beyond 19 meters it is not effective because tan hyperbolic ml, that is, I have taken 2.65 ml of 2.65. So L of copper is 0.19 meters and length of aluminum is 0.13 meters, but in spite of using 13 meters it can dissipate only 5.6 watts. So it is ideal to use either copper or aluminum. Stainless steel is definitely not good because it is going to dissipate only 1.6 watts and it is not effective beyond a length of 0.04 meters. So here copper is effective up to 0.19 meters and it can dissipate a heat of 8.3 watts. So we have to take this into consideration. So we define what is called as fin efficiency by comparing the Q fin with the Q fin maximum, that is assuming that infinite thermal conductivity, the temperature is going to be uniform. So if I derive that, I get efficiency of the long fin as 1 by ml and insulated efficiency as tan hyperbolic ml by ml. So this is how you can get the efficiency. You would like to keep the efficiency as high as possible. Now, so usually we would not like to go with a fin efficiency greater than 90%. So using these values, you can choose your ml such that your efficiency is of the order of 90% depending on the fin tip condition what you are using. Now like this we have derived only for standard cases, but one can derive. There is a book by Krause which is heat transfer in extended surfaces itself. There is a textbook where it's like a data handbook where for various shapes, for example, you see this is circular pin fin, this is another type of fin, this is another type of fin. For each of these fins, the efficiency of the fin with as a function of geometric parameters and the heat transfer coefficient and kT and zeta. Zeta is, you see here, L plus T by 2 square root of H by kT involving geometric parameters, heat transfer coefficient and thermal conductivity. We can get the efficiency of the fin for different shapes. You do not have to sit and calculate the efficiency of the fin for different shapes. So you can just simply use this chart or the graph and get the efficiency of the fin. I have cooked a problem, we will be solving a problem also at the end. So now for example, this is the circular type of fins which is very common in compact heat exchangers. So you can see that you can use L plus T by 2 square root of H by kT, and the R2, that is the radius, the R2, this is the R2 and R1. As you go on increasing R2 for a given thickness and given R1, how does the efficiency improve? It is plotted here, and you can just use this graph and calculate, take the efficiency of the fin and design your fins and fix how many number of fins you can use. So there is a problem to that extent, but before we solve that problem, there is a concept called fin effectiveness. So what is that fin effectiveness? So let us derive or understand what is called as fin effectiveness. Fin effectiveness, that is, if you have a base and this is your area of the base and this is the heat transfer which is taking place from this base, that is Q dot no fin, okay, that is Q dot no fin. But on the other hand, if you have put a pin fin, okay, so then there is heat transfer taking place from the fin. So effectiveness of the fin is equal to Q dot fin divided by Q dot no fin, Q dot no fin. So effectiveness of the fin is equal to Q fin divided by H into area of the base, this is area of the base, into Tb minus T infinity, where Tb is the base temperature, T infinity is the fluid temperature. So now what is the physical significance? If effectiveness is equal to 1, what does that imply? So putting fins are not adding any extra heat transfer, they are not taking away any extra heat transfer, okay. And if effectiveness of the fin is less than 1, this implies that fin actually is taking away the heat less than no fin. That is not, it is possible only when if fins are acting like insulated surfaces or insulators, acting like insulation, okay. So there is, the fins are, that is possible only when thermal conductivity of the fin is very less, like plastic or something. So if the effectiveness is greater than 1, if effectiveness is greater than 1, that is what is the situation what we want. We want have efficiency of the fin very large or closer to 1 and effectiveness of the fin greater than 1. So now, so effectiveness of the fin, let us try to find the relation between efficiency, fin efficiency and fin effectiveness. Fin efficiency and fin effectiveness. So, effectiveness of the fin is equal to Q fin divided by Q no fin, that is Q fin divided by H into AB into TB minus T infinity. Okay. And efficiency of the fin is equal to Q fin divided by Q fin maximum, how much maximum a fin can take away if it is having infinite thermal conductivity, that is Q fin divided by H into area of the fin into TB minus T infinity. Okay. So, now if you compare these two equations, if you compare these two equations, that is if you substitute for Q fin, that is efficiency of the fin is equal to Q fin equal to effectiveness of the fin into H into AB into TB minus T infinity, that is from here I am writing. Okay. That is Q fin equal to effectiveness, that is this equation I have put, divided by H into area of the fin into TB minus T infinity. So, TB minus T infinity. So, you get efficiency of the fin equal to effectiveness of the fin into AB by A fin, or effectiveness of the fin equal to area of the fin, because you get the efficiency of the fin from those graphs. So, that is why you can compute the effectiveness once you know the fin efficiency by just multiplying the area of the fin divided by area of the base. Okay. So, that is what it looks like this. So, this is the maximum fin efficiency if you have, that is whole of the fin is sitting at the same temperature, that is possible, then only maximum fin heat transfer takes place, but the actual fin is having this. So, this is Q no fin and the Q fin, this is comparing the fin efficiency, this is giving the fin effectiveness. So, we are now able to get the fin effectiveness once you get the fin efficiency. Now, the question next is, effectiveness, we have to get some fin effectiveness is equal to Q fin divided by Q no fin. That is, if I take long fin, if I take Q long fin, if I take infinitely long fin, that is TB minus T infinity into square root of HPKAC divided by H into AB into TB minus T infinity. So, if I take AC equal to AB, then H TB minus T infinity gets cancelled. So, I get KAC divided by HP, sorry KP divided by HAC, KP divided by HAC. Okay. So, that means this is having very important implication, we need to understand this. You want to increase effectiveness of the fin as high as possible. That is possible if you take very high conductive material, that is copper is better than aluminum, which is better than stainless steel, which is better than any plastic. Plastic effectiveness will be less than 1. Now, if the effectiveness has to increase, P by AC has to be very large. That means perimeter should be greater than cross sectional area, that is possible only when you use slender fin. It has to be slender fin, thin plate fins are very effective because its effectiveness will be very high. Or And another thing which is counterintuitive is heat transfer coefficient has to be low. It is not counterintuitive, but we usually think higher H is good, but you see that effectiveness of the fin is only is good in those situations where H is low. That means fins are good either in natural convection or in forced convection where you are using gases or air, because heat transfer coefficient in these cases with gases is generally lower than the heat transfer coefficient in liquids in forced convection. So if you have, let us say, tube in tube heat exchanger, so if you have fluids, if you have air flowing here and if you have water flowing here, you would definitely put fins on the side where air is flowing, because the fins on the air will be more effective. So that is why in the car radiator fins are put. In the car radiator fins are put in the very first graph. The fins are placed on the gas side. You see here, this is on the these fins are put on the gas side. This is on the gas side, there is a fan which will cool, but this is air cooled, but the liquid is flowing inside the tube. So fins are not put inside the tube because the heat transfer coefficient inside the tube is high. So here on the outer surface where the air is flowing, the heat transfer coefficient is less, so fin effectiveness will be large here. That is the reason why we use the fins on the side where the heat transfer coefficient is less. So to understand all of this, let us quickly solve a problem. But before we solve the problem, so let us try to get the Q total, the total fin, the heat transfer, the Q total fin is equal to Q unfin, because here the heat transfer is taking place both from this base surface where there is no fin and also from the area of the fin. That means Q unfin equal to H into area of the unfin into Tb minus T infinity. But Q fin equal to efficiency of the fin into area of the fin into Tb minus T infinity. So that means Q total fin is equal to Q unfin plus Q fin is equal to H area unfin into Tb minus T infinity plus efficiency of the fin into H into area of the fin into Tb minus T infinity. Okay. So that is H into area of unfin plus efficiency of the fin into area of the fin into Tb minus T infinity. This is what you get as Q total fin. So effectiveness of the fin is equal to Q fin, that is Q total fin divided by Q no fin, that is H into area of unfin plus efficiency of the fin into area of the fin into Tb minus T infinity divided by H into area of no fin into Tb minus T infinity. Okay. So let us use this and solve a problem. So what is the problem comprising of? Steam in a heating system flows through tubes, okay, whose outer diameter is 3 centimeter and whose walls are maintained at a temperature of 125 degrees Celsius. The circular aluminum pin fins of outer diameter D2 is 6 centimeters, that is this R2 is 3 centimeters, R1 is 1.5 centimeters. The thickness is 2 mm and the space between the fins is 3 mm, these are circular pin fins, and thus there are 200 fins per meter length of the tube. the heat is transferred to the surroundings at 27 degrees Celsius, and the combined heat transfer, that is both radiation and convection heat transfer coefficient, is 60 watt per meter square degree Celsius. Determine the increase in the heat transfer from the tube per meter length and as a result of adding fins. So now what we will do is area of the no fin. If I take area of the no fin, area of no fin is equal to pi d1 into L. Pi into d1 is point, that is a bare pipe, that is 0.03 into 1. So you get 0.0942 meter squared. Now Q no fin is equal to H into area no fin into TB minus T infinity. H is 60 into 0.0942 into TB is 125 minus 27. So you get Q no fin equal to 554 watts for 1 meter. Now let us take up fins. For taking up fins, I need to get the efficiency. So for getting the efficiency, I need to compute R2 plus T by 2 by R1 and L plus T by 2 into square root of H by KT. So let me do that, otherwise you may get confused. So that is R2 plus T by 2 divided by R1. R2 is 30, that is 60 by 2, 30 plus thickness is 2 by 2, R1 is 15. So I am taking both in the same units, so I am not bothered of converting them into meters. L plus T by 2, here I have to convert it into meters, into square root of H by KT is equal to L is R2 minus R1, that is 0.015. L is R2 minus R1 plus thickness is 2 into 10 to the power of minus 3 mm. I am converting into meters, that is why I have multiplied by 10 to the power of minus 3 into square root of H is 60 divided by K is 180, it is made of aluminum, into thickness is 2 into 10 to the power of minus 3. So whole of this gets me as 2.21. Using these two values, I have to take, because I am having efficiency plot where I have this L plus T by 2 into square root of H by KT as my x axis, and the y axis is the other parameter. If I see that R2 you have 0.21, so that is somewhere here 0.21, and R2 plus, that is 2. So you can take the second graph, so somewhere it will come here. So you will get efficiency as 0.95. So if you take the efficiency as 0.95, okay, efficiency as 0.95, so you take Q total fin is equal to H into area of the fin plus efficiency of the fin into area of the fin into TB minus T infinity. Now area of the fin, what is the area of the fin? That is pi into R2 squared minus R1 squared into 2. So to make you understand, let us go to this figure. So if you see here, the fin surface area is the top surface area, that is pi into R2 squared minus R1 squared, top and bottom, that is why you have 2, and again you have 2 pi R2T, that is 2 pi R is the circumference of the ring and the thickness is the, okay, this is your, this area is 1 and then this thickness. So you have 2 pi R2 squared minus R1 squared plus 2 pi R2 into T, this is the thickness T. Okay. So now if you substitute 2 pi into R2 squared is 30 into 10 to the power of minus 3 squared minus R1 squared is 15 into 10 to the power of minus 3 squared plus 2 pi into 15 into, sorry, R2 is 30 into 10 to the power of minus 3 into thickness is 2 into 10 to the power of minus 3. So, you get area of the fin as 0.00462 meter squared, and area of the unfin is pi d1 into s, that is the left out space, that is pi into d1 is 30 into 10 to the power of minus 3 into s is 3 into 10 to the power of minus 3, that is 0.000283 meter squared. So, if I substitute that into this equation, Q total fin is equal to H. What is my H? H is 60 into area of the fin is 0.000, this is area of the unfin, this is area of unfin, 0.0000283 plus efficiency of the fin 0.95, area of the fin 0.00462 into TB 125 minus 27. So, you get this as 27.46 watts, but you have 200 fins. So, if you multiply by this 200 fins, you get 5492 watts, but your Q no fin which we found was only 554 watts. So, the Q increase is Q fin minus Q no fin is Q fin is 5492 minus 554. So, you got 4938 watts, or effectiveness. What is the effectiveness of the fin? Effectiveness of the fin is Q fin divided by Q no fin, that is 5492 divided by 554. So, you get 9.91. You see, the efficiency of the fin was 95% and effectiveness of the fin is 9.91. So, compared to no fin case, it is almost 10 times better than increased, 10 times the heat transfer rate has increased, and the efficiency of the fin, I have not used a very long fin which is ineffective, which is efficiency of the fin is almost near about 100%. So, this increases the heat transfer, by almost 10 times in my steam tubes. So, that is the advantage of putting the fins. So, with this we come to the conclusion of fins, and by now you should be able to compute or design several fins. So, in the assignments we will give various combinations of fins where you will be comfortable in applying these relations. So, I strongly recommend that you please derive all of these yourself once, so that you are confident. In real life applications you may get beyond this, but once you have done this, any new given boundary condition you will be able to approach that problem with confidence. Thank you.